Welcome to Spaceverse, your portal to cosmic adventures. Since the James Webb Space Telescope began its mission, it has made a series of groundbreaking discoveries that have deeply challenged our understanding of the early universe. One of the most remarkable findings is the identification of ancient galaxies that seem surprisingly well formed for their supposed age. These primordial galaxies appear far too large, highly evolved, and structurally advanced for the time periods in which they are observed. This unexpected maturity is in stark contrast to the predictions of the standard model of galaxy formation, which suggests that such galaxies should still be in their infancy, characterized by small sizes and irregular structures. Their presence raises significant questions about the accuracy of our current models for the formation and evolution of the universe. But what if the issue lies not with the galaxies themselves, but with the very way we understand cosmic history? Could the Webb telescope's observations be pointing us toward a paradigm shift in our perception of the universe? Rather than simply revealing anomalies in distant galaxies, could it be offering us a new way to view the very fabric of reality? One potential key to solving this puzzle could lie in the concept of redshift. As the universe expands, light from distant galaxies stretches, shifting to longer wavelengths, a phenomenon known as redshift. The further away a galaxy is, the more its light is redshifted, which allows astronomers to estimate both its distance and the time when the light was emitted. JWST has pushed the limits of this capability, peering back over 13.5 billion years into the universe's early history, just a few hundred million years after the Big Bang, which is believed to have occurred around 13.8 billion years ago. According to the standard cosmological model, galaxies from this early period should be small, chaotic, and forming in an irregular manner. However, JWST has revealed something far more surprising: large, well-organized galaxies with intricate structures, galaxies that appear much more evolved than expected. This discovery is forcing scientists to reconsider long-standing theories of cosmic evolution and may suggest that our models of galaxy formation are missing some crucial piece of the cosmic puzzle. In essence, these findings challenge not only our understanding of the specific formation of galaxies, but also the broader framework through which we view the universe's history. Could it be that the standard assumptions about how galaxies evolve over time need to be rewritten? Or is there a deeper, more fundamental shift in our understanding of the cosmos that these observations are hinting at? JWST's discoveries may be the first step toward rethinking everything we know about the universe's origins, its structure, and its evolution. Yet what's perhaps even more intriguing is what recent observations have revealed. The JWST Advanced Deep Extragalactic Survey examined 263 early galaxies and discovered a strange, synchronized cosmic movement. This peculiar finding has led some scientists to propose that our entire universe might reside within a black hole. Welcome to truly uncharted territory. This is the frontier of your space. A new study based on JWST's deep space data has uncovered a cosmic puzzle. A significant number of early galaxies appear to be spinning in the same direction. By studying the curvature of their spiral arms, astronomers were able to determine their rotational orientation. Remarkably, the data shows a preference for one dominant spin direction. This is a profoundly intriguing observation because, in a universe that is typically understood to be governed by randomness and symmetry, two central pillars of current cosmological models, the rotational directions of galaxies should theoretically be evenly split between clockwise and counterclockwise. This is based on the assumption that such rotations are random and not influenced by any overarching cosmic structure or force. However, the findings from the James Webb Space Telescope are offering a radically different picture. The telescope's observations have revealed a surprising consistency in the rotational directions of galaxies, with a clear preference for one direction over the other. This is not only unexpected, but it also challenges the conventional wisdom of a random, symmetric universe, suggesting that the structure of the cosmos might be far more intricately interconnected than previously believed. If these findings are confirmed, they could force us to rethink our understanding of the universe on a fundamental level. The observed consistency in galactic rotations doesn't just question the randomness assumed in our cosmological models, it hints at something much deeper, something potentially mind-bending. The universe might not be the chaotic, randomly structured system we have always thought it to be. Instead, the coordinated movements of galaxies could indicate that there are larger forces at play, forces that we have yet to fully comprehend. This could point toward the possibility that the entire cosmos operates according to a more complex, underlying principle that we are only beginning to unravel. And if these synchronized galactic motions are not merely an anomaly but a widespread, systemic feature of the universe, it opens the door to even more radical ideas. One such idea is that our universe itself could be enclosed within a massive black hole, a concept that, if proven true, would challenge the very foundations of modern physics. Imagine the implications of such a theory. Space, time, and reality itself would no longer be the vast, ever-expanding void we once thought it to be, but rather a construct of incredible complexity, governed by the same forces that shape black holes. This perspective would fundamentally alter how we understand the universe's origins, its structure, and its very existence. To fully grasp the potential of this theory, we need to delve deeper into the physics of black holes. Black holes are formed when matter collapses under its own gravitational pull, creating a singularity, a point of infinite density. Surrounding this singularity is the event horizon, the boundary beyond which not even light can escape. Anything that crosses this point is lost to the outside universe, invisible and imperceptible to any observer. The internal structure of a black hole, however, remains one of the greatest mysteries in astrophysics. What lies beyond the event horizon, within the black hole itself, is something we can only speculate about, as no information can escape from this region to reveal its secrets. This is where the concept of black hole cosmology, or Schwarzschild cosmology, comes into play. This theory proposes that our entire observable universe could exist within a black hole located in a much larger, higher-dimensional parent universe. According to this idea, the universe we see, our galaxies, stars, planets, and even the laws of physics as we understand them, could be the result of the extreme conditions inside a black hole. Essentially, the Big Bang, the origin of our universe, could have been the result of a massive cosmic event that occurred within the confines of a black hole in a parent universe. If this concept holds any truth, it would radically shift our perspective on the nature of existence, offering a new way of thinking about time, space, and the limits of our observable reality. In this model, the observable universe would be a bubble of space-time constantly expanding inside the black hole. The event horizon of this cosmic black hole might be the boundary beyond which we could never see or interact, but inside it, all the galaxies, stars, and cosmic phenomena we observe today would have originated. This theory challenges not only our understanding of the universe's beginning, but also the very structure of space and time as we perceive it, suggesting that what we consider the edges of our universe could be far different than anything we've imagined. It could open up entirely new questions about the relationship between different universes, the potential for other black holes to house their own universes, and how the cycle of cosmic birth and rebirth could work on a scale far beyond our current comprehension. This perspective offers a new interpretation of the Big Bang. According to the standard cosmological model, the universe originated from a singularity, an infinitely dense point, similar to the core of a black hole. If our universe formed inside a black hole in a larger universe, then the Big Bang wouldn't be an explosion into an empty void. Instead, it would represent the moment when matter collapsed and created a black hole, leading to the birth of a new universe within. This idea suggests that each black hole in our own universe could serve as the seed of a separate universe. It could also provide an explanation for the finely tuned nature of our universe's physical constants. If only black holes that produce stable, life-supporting universes persist, then universes like ours might be more common in a vast multiverse formed by black hole births. Scientists believe this theory could help solve several enduring cosmic puzzles. For instance, black holes are known to possess extraordinarily high entropy, which could relate to the immense amount of information contained within our universe. Another important element in this idea is something called torsion. In extended versions of general relativity, like the Einstein-Cartan theory, torsion is a property linked to the intrinsic spin of particles, and it can influence the way space-time curves. Some versions of these theories suggest that at extremely high densities, torsion could create a repelling force strong enough to counteract the infinite collapse of matter, essentially preventing singularities from forming. In such a case, instead of matter collapsing into an infinitely small point, a black hole might undergo a big bounce where the extreme core rebounds and begins to expand. This process could theoretically create an entirely new universe within. The scientist also noted that a rapid rebound following such a big bounce could have sparked the expansion of our universe, an event we now describe as the Big Bang. In this view, the Big Bang wasn't an explosion from a singular point of nothingness, but rather a dramatic resurgence from within the core of a black hole in a parent universe. This idea, if proven, would completely reshape our understanding of how the cosmos began. It implies that the birth of universes is part of a continuous, self-sustaining cycle, where black holes serve as the cradle for new realms of existence. An additional and equally fascinating possibility is that our universe may possess a preferred axis, a kind of cosmic direction. Studies of large-scale structures in the universe have revealed patterns in the way galaxies align and move that don't appear to be entirely random. This phenomenon, known as cosmic anisotropy, runs counter to the long-held cosmological principle, which assumes the universe is isotropic and uniform when viewed on a grand scale. If there truly is a favored direction in space, it could hint at undiscovered physics, potentially linked to the nature of our universe's birth within a black hole or to interactions between fundamental forces on a cosmic level. Moreover, the detection of massive, mature galaxies in the very early universe continues to defy established models of cosmic evolution. However, while the black hole universe theory is certainly compelling, it's important to remain open to alternative, perhaps simpler explanations for these unexpected findings. It's possible that some of our earlier cosmic measurements might be inaccurate. For example, we might have miscalculated the rotational speed of the Milky Way. Or perhaps the universe is actually older than our current estimates suggest. Regardless of the explanation, one thing is becoming increasingly clear. The universe is proving to be far more bizarre and complex than we once believed. The discovery of inconsistent galactic spin patterns and unusual cosmic structures will likely lead astrophysicists to revisit and revise key aspects of modern cosmology. What's your take? Could our universe actually exist inside a black hole? While that theory is undeniably intriguing, another recent study introduces a completely different idea that our universe might have a twin, a kind of mirror realm where time flows in reverse. But if not, it's definitely worth checking out. Now, have you ever come across the concept of Occam's razor? It's a logical principle often used in science, which suggests that the simplest explanation is usually the most likely. For example, if astronomers were to notice strange lights on a distant planet, they shouldn't jump to the conclusion that aliens are involved. Occam's razor would encourage them to explore more straightforward possibilities first, like natural atmospheric effects or geological activity. So why mention Occam's razor here? Well, many inflationary models, those that attempt to explain how the early universe rapidly expanded, predict that this event should have generated long wavelength gravitational waves or subtle ripples in the fabric of space and time. If we were to detect these primordial waves, it would strongly support the theory of cosmic inflation. Now, to clarify, gravitational waves have been detected, but only from cataclysmic events like black hole mergers and neutron-star collisions. Despite numerous high-precision experiments, no evidence of the primordial gravitational waves predicted by inflation has been observed. With each new failure to detect them, more versions of inflation theory are being called into question. To be fair, inflation does provide some compelling solutions, such as explaining why the universe appears so uniform across vast distances. But it also brings up new problems. For instance, what kind of energy field could have driven that inflation in the first place? Inflation also assumes that the universe began with extremely specific conditions, yet offers no clear reason why those initial conditions existed. Some inflation models even propose the idea of infinite bubble universes, an idea that, while fascinating, opens up difficult philosophical and scientific questions about what can actually be tested and what defines physical reality. Disregarding Occam's razor in this context would be like assuming there are no simpler explanations to explore. That's exactly the mindset Neil Turok, a renowned theoretical physicist and holder of the Higgs chair, aimed to challenge. Together with his collaborator, Lamboll, 2Rock developed a fresh theoretical framework that attempts to answer deep cosmic questions without depending on the standard inflationary model or string theory. By applying Einstein's general theory of relativity and our current understanding of physics to trace the universe backward through time, we reach a moment where space and time compress into a single point known as the initial singularity. To better understand this incredibly dense and hot early state, theorists like Nobel Prize winner Roger Penrose identified a special symmetry present in the behavior of light and massless particles. This is known as conformal symmetry. Unlike ordinary matter, these particles don't seem to be affected by the extreme compression of space at the universe's origin, allowing them to escape the harsh effects that dominate the Big Bang environment. Think of it like a flexible rubber sheet with a picture drawn on it. If you stretch or compress the sheet, the drawing might grow or shrink in size, but its shape remains unchanged. Conformal symmetry works in a similar way. It suggests that certain fundamental aspects of the universe stay consistent, regardless of how the universe itself is scaled. This could mean that the universe's large-scale smoothness might not require an explosive inflationary burst, but could naturally result from this underlying symmetry. In their model, the Big Bang isn't just a beginning, it functions as a kind of temporal mirror. Time flows forward on one side of this mirror and backward on the other, like a cosmic reflection. This idea aligns with a deeper concept in physics known as CPT symmetry, a fundamental principle stating that the laws of physics remain the same if three properties, charge, parity, and time, are all reversed at once. To visualize it, imagine the universe as a grand theatrical performance governed by these three rules. Charge swaps matter for antimatter, parity flips the scene as though viewed in a mirror, and time runs the show in reverse. If you flip all three together, switching charges, mirroring everything, and reversing time, the performance still unfolds exactly the same. The universe doesn't miss a beat. The physics stays perfectly intact, no matter how the stage is set. Still, the clear imbalance between particles and antiparticles, along with the one-way direction of time in our universe, makes it seem like CPT symmetry might not hold. But the mirror universe idea brings this symmetry back into the picture by proposing a universe that is a reversed reflection of our own. In this counterpart, time flows in the opposite direction and antiparticles are more common than particles. This mirror universe doesn't necessarily have to exist physically, it might just be a mathematical model designed to preserve symmetry at the moment of the universe's birth. Their model also offers a potential explanation for dark matter. Neutrinos, tiny, fast-moving particles, always spin left-handed. However, their theoretical counterparts, heavy right-handed neutrinos, could be stable and interact only via gravity, making them promising dark matter candidates. Using the mirror universe framework, 2Rock and Bohl calculated that these right-handed neutrinos could indeed make up dark matter. According to their theory, if this is the case, then at least one of the three types of known light neutrinos must have zero mass. This idea is currently being tested by looking at how galaxies and large-scale structures are distributed across the cosmos. Studying how matter clusters throughout space might give us insight into neutrino masses, providing potential support or refutation of this dark matter theory. The researchers also addressed another puzzle: why the universe looks so flat and smooth on a grand scale. They used entropy, a concept related to the probability of certain configurations, to explain that a flat, quickly expanding universe with a small positive acceleration is actually the most likely outcome. Moreover, they demonstrated that quantum fields, rather than inflation, could account for the small variations in cosmic density. Still, further investigation is necessary to fully validate the new theory. 2Rock, whose team shared their findings in the Annals of Physics, explained that imagining the Big Bang as a kind of mirror offers a compelling way to account for many cosmic features that otherwise seem to contradict fundamental laws of physics. The progress we've made leads me to believe there are likely simpler alternatives to the prevailing standard model, which has become more of a constraint than a guide, he wrote. While this theory still requires extensive testing and validation, 2Rock emphasized that even if it turns out to be incorrect, it serves as a reminder that we shouldn't overlook more straightforward explanations. So, what's your take on all this? Drop your thoughts in the comments. From bouncing singularities to right-handed neutrinos, the cosmos keeps challenging what we thought we knew. If you're fascinated by theories that turn reality upside down, hit that subscribe button. This is Spaceverse, where we explore the universe, one mind-bending idea at a time.